Thank you very much. What does empirical mean? It means I don't take into account any physics at all. And if I try to take some physics into account, it doesn't make it any better. So in my model, we have mass, m, which is just a function of the number of protons, the atomic number, and the number of neutrons. And hopefully, from these two rather fundamental parameters, we can calculate the properties of any nucleus. And not just atomic masses, actually. You can apply it to atomic radii or to spin. It's just an equation of two independent variables. Why are we interested in atomic masses? We can measure atomic masses to an incredible 9 significant figures. And we have thousands of these measures over the last century or so. And consequently, we can test our theoretical models of the nucleus very accurately on the basis of the very accurate experimental measurements. In particular, astrophysicists are very interested in knowing where the neutron drip line is. That is to say, the very unstable neutron-rich isotopes which are formed in a supernova, and we need to know whether or not they can capture more neutrons. And if we can do that calculation accurately, and obviously we can't measure the atomic masses of these exotic nuclei, we can then model supernovae and calculate the abundance of elements created in the universe. I want to distinguish two definitions, which I call local and global, but this is actually quite a common notation in the nuclear mass field. A local equation is one rather like this one here, in which a mass can be calculated just in terms of its nearest neighbors. That's rather remarkable. No physics involved, it just happens to work. And people have been wondering about this for about, well, certainly since the 60s, so that's 70 odd years. In contrast, a global relation is an ordinary analytic equation based on the function of some kind of mathematical expression. And obviously this does not depend on knowing any particular masses, it just depends on the parameters we have inside these. Now here's an example of a local relation. I've just taken a not quite random block from the table of isotopes, and if we calculate the difference in masses, basically this mass plus this mass, it happens to be equal to this mass plus this mass, and consequently we can find any one of those masses knowing the other three. And we can do it to an accuracy of 10 keV, which is remarkable. But I have to admit, I chose this example deliberately. In practice, it's not nearly so good, and I think, if I was really honest, this would be on average about 500 keV. Even so, that's quite good, but not nearly good enough. Dr. Bowen mentioned the Weizsäcker equation, which is a semi-empirical formula. It takes into account the short-range attractive power of nucleons, which are the so-called bulk or volume effect. You subtract a surface effect because the nucleons near the surface don't have so many neighbors, and therefore they're bound more loosely. There's a Coulomb repulsion effect. There's a symmetry effect. So if the neutrons are not matched up exactly with the number of protons, the protons with the neutrons, there's going to be some more negative energy. There appears to be an odd-even effect, and the odd-even effect, according to this formula, is whether the number of neutrons or the number of protons is odd. And that produces an RMS error over about 3,000 nuclei of about 3.5 MeV, and that was the situation of about 80 years ago or so. So this is a rather very old-fashioned model, but it was adequate at the time. The number of measurements of nuclei, of course, was only about 100 in those days. Now it's 3,000. For my analysis, I've used the very latest evaluation of atomic masses, which is calculated by the very, I think there are over 3,000 parameters in the, oh wait a minute, there are 3,000, 3,000 measurements without any doubt, because there are well over 3,000 known nuclei. I use a subset of these, only 2,300 or so, and that's because in the model, in most models, the data is restricted to atomic number greater than 6, neutron number greater than 10, and I think people chose this simply to make their model look a little bit better. We're obliged to follow the same restrictions. Actually, in the model I'm going to present, there are no such restrictions. You can have more protons and neutrons if you want to, and you can go down all the way down to deuterium and calculate binding energies. So the model I'm going to show you is very generic indeed. I do recommend, if you're going to predict atomic masses, you use the very latest database. And if anyone wants a copy of this, I'll be very happy to give it to them. The experimental errors are extremely variable. And because scientists don't like to be proven wrong, they actually are rather conservative. According to my comparisons of the observed against experimentally observed and the theoretically calculated, my guess is that quite a lot of nuclei are in fact much more accurately measured than people say. But that means that they're not normally distributed, so you can't apply the standard statistics to them, which makes the comparison of errors rather difficult. So in the work I'm going to present, I don't consider any experimental measured isotope whose accuracy is worse than 125 keV. That is because my aim is to get around 100 keV of accuracy in the model itself. So if we include in the model widely, very inaccurate results, they simply distort the model. In the literature, there's quite a lot of discussion of so-called model error, which quadratically subtracts the experimental errors from the deviations in the model itself from the experimental data. I'm not sure this is a particularly good technique. The entire papers have been dedicated to the problem, particularly because of the non-normal distribution of the experimental errors. If everything was normally distributed, the statistics would work perfectly, but they don't. In fact, because of the overestimation of errors, you can actually find that the model error gets reduced to 0, and we all know that not even my model is perfect. What is the nature of the data we have which nature's given us? What are the observed energies? And this is a rather unusual diagram. Basically, this contains every single nuclear mass measurement. But it's not the absolute mass, it's the S2N, which is the separation energy for 2 neutrons. Why do we present data in this way? First of all, it eliminates any odd-even effect, because if you've removed 2 neutrons, you've got the same oddity or evenness, parity of the nucleus that we had before. Secondly, removing neutrons doesn't change the Coulomb energy very much. So this is a very convenient way of looking for systematic trends in atomic masses. And the data here is incredibly complicated. We can see discontinuities, like this line here, this line here, this line here, this line here, this line. And these are all the equivalent of magic numbers. So when we go from one shell to the next shell, there's effectively a discontinuity. And this demonstrates really that the data we have to predict is remarkably complicated. Look, there's something very strange going on in the middle here, but it's systematic. So we want some systematic way of predicting these masses. I wrote my own software because I'm a programmer by profession. It's written in C. It's about 4,000 lines. And in it, I analyze 100 different models. I like to compare one model with another. So if you've got a model which could be reduced to a reasonable form, I will do my best to analyze your model. It's taken me about 25 years to develop this, but I'm pretty satisfied with it now. As I say, no account is taken of underlying physics. No nuclear theory is involved, but given that this kind of approach has been tried in the past, there's a very long review, an early paper by Garvey and Kelson in 1969, and they tried to explain why it worked so well, but I think it was a lot of hand-waving. So here's one of the local relations I mentioned. This is, in fact, the Garvey-Kelson relation published in 1969, as I just said. If you add the mass of this one, subtract that one, add that one, you get a total of 0. This is rather more sophisticated than the previous diagram I showed you. This has an error of, say, 314 keV, rather better than the 500 we saw before. And these workers noticed that because the sum of every column is 0, and the sum of every line is 0, and the sum of the diagonals is 0, they intuitively realized that the global formula corresponding to this is really quite simple, a function of the number of protons, function of the number of neutrons, and the function of the number of the atomic mass number. And this was way back in 1969, quite remarkable, I think. A more recent paper by the Chinese. The Chinese have taken responsibility for the atomic mass evaluation now. Actually took a formula first noticed by Janicke and Komai, and I rediscovered this formula myself 10 years later. In fact, at the 1995 conference in Monte Carlo, I produced this formula again. So it's fairly obvious in some ways. The only trouble is, though, you've got an awful lot of parameters, 583. The reason for that is every one of these so-called functions, being functions of integers, we don't know what the function is, and so these workers used a table lookup, and you generate a really quite complicated model, but it's a fairly accurate model. As you can see, the RMS error is now down to 206 keV. So my strategy has been, first of all, to identify the best local relationship. And again, I use a computer to go through every possible local relationship which might exist and find the best one. And this is not quite the best, but it's quite a good one. Again, we have the columns all adding up to 0. But this time I have to put a parameter in there. And similarly, the lines. In fact, it's rather symmetrical. And I noticed one day when I was waking up in the morning that this actually corresponds to a differential equation. It looks rather complicated, but if we were to just look in one dimension, this would be a second-order differential equation, an approximation to the second derivative, that is. And so that is the corresponding differential equation. And if you do that, you get a pretty good model, but we can improve it quite a lot more. So I think I've covered that point. However, if you make a very minor change to the local relationship, by having these blank columns, a blank column simply means 0 for the parameters here. The error comes down to 82 keV. That is absolutely remarkable. As far as I can tell, the best published relationship for a global formula is around 300, something like that. Well, we saw 200 for the Chinese. So that hints there's something rather strange going on, and it's accounted for by this term here. In the previous slide, I showed this was 0, but if we make it some kind of odd-even effect, and It's not even effect, notice, not based on atomic number or neutron number, but on a mass number. In other words, it's a secondary odd-even effect, because the primary odd-even effect has already been taken account of in the function of n or z, which we saw earlier. An even better one is this. We've got it down to 71 keV now. In fact, this is just the same local relation we saw before, but one is rotated by 90 degrees and added to the other, so you take an average, effectively, of two local formulae. And we could try working out a global formula for it. So I've added an odd term here, which I haven't quite defined, but we saw it earlier. Well, if fourth order works, let's try sixth order. And now we can get an RMS error of an incredible 91 keV. This is without knowing any a priori knowledge about the nuclear at all. But unfortunately, I think it's likely that at the extremes of unknown areas of the table of isotopes, we're going to find even this is not quite so good. But the defects in the model are certainly shared by every other model. So I still think this is going to be the best. However, I'm a bit concerned that we have 800 parameters here. Okay, I think I'll skip that. How do we reduce the number of parameters to a more reasonable level? Well, the crazy functions, the point functions, in many cases are fairly straight. So you could just remove some of those points and interpolate to find out what they should be. And consequently, if you do that, you get a much reduced number of parameters. And here's a summary of some of the results of so-called global models. As I said, the von Weizsäcker formula had an error of 3.5 MeV with 6 parameters. Of course, there are several varieties of it. Dr. Bowen talked of 5 parameters. The Garvey-Kelson formula of 1969 had 524 parameters, and they brought the error down to 314. Bow, this is the finite range droplet model, 656 keV of error, so not particularly good, really. Again, this is another global formula of the Chinese I mentioned, 206. And here are 3 of my results. This is the unadulterated formula without any interpolation, but with 800 parameters. But you could use that down to the 500s, and the error doesn't get much worse. So personally, I'm more inclined to think that these are going to be better predictors of atomic masses. I think that the Garvey-Kelson local relations had a very major role to play in verifying atomic mass measurements. They're still used today because they're so much more accurate, and they don't depend on any physics. But the corresponding global equations really are less accurate and prone to fail for isotopes far from stability. I think there are still too many parameters, and there's no physics. But if we add expressions such as Coulomb repulsion, asymmetry, and odd-even effects, they make absolutely no difference. So they're already incorporated in the global functions. Anyway, I think after 50 years of original work, an improvement is overdue, and I hope this model is going to do exactly that. I think this is actually the most accurate model of any mass predictor. It's not widely published, though it has been published in Reviews of Modern Physics or something. I can't help saying this. Lies, damn lies, and statistics. Given enough parameters, you can prove anything you like. So you must ensure that that you have far more observations than parameters. This is why I insist on trying to get those parameters down. So I think that's probably the end of my talk, isn't it? Not quite. The astrophysicists ask for 250 keV of precision in estimating atomic masses. I give them around 100, so I think I've satisfied their requirements.
Actually, it's not a question, it's a comment. You mentioned if you add parameters, you can fit to anything you want, which is true, but there are mathematical formulas which justifying the addition of parameter, and you might want to test that. One of the lightest one is the Akaike criteria that you can, if you pass it, that shows the adding parameter is justified. And you can go one by one and you find the cutoff limit when your addition of parameter is not justified. That's mathematically easily.
We need to remember that the parameters are in fact entire functions. So maybe the statistics don't quite work like that. But what I have done is I systematically remove some of the points in the functions to try and reduce the number of parameters. And another thing I do is cross-validation. I create the model on a subset of the, say, 90% of the observations and try and predict the other 10%. So I have a good feeling for the predictive power of the model. And you can do that for different subsets, of course.
I did not question that.
One of the most difficult calculations is the calculation of the alpha particle, because that's a much lower binding energy than the rest of the elements. Can you give me the number you got on that one?
There are no restrictions as to the range and applicability of the model. And I mentioned in particular that when there is a proton-rich nucleus or a very light nucleus, the model works correctly. And a lot of other models exclude this area simply because the models break down. They tend to break down at extremes.
Okay, I would like to take advantage of having Bill on stage to thank him for his presentation, but as well for all the work he's been doing with Claudio Pace in organizing that very good conference we are attending all